In the previous couple of lectures, you learned about sensor signal conditioning, preparing a sensor's output to make it stable, clean, and suitable for further processing. Part of that process often involves filtering noise, but the concept of noise filtering is broader. Think of noise as a subset problem within the broader objective of conditioning a signal. When working with real-world sensors, we rarely get a perfect, clean signal. Instead, we get a raw analog output that may need to be modified before it's useful to a microcontroller or data acquisition system. This preparation process is called sensor signal conditioning. Sensor signal conditioning usually focuses on one specific signal source, such as a temperature or pressure sensor, and prepares that signal for a system to use. Noise filtering, on the other hand, is a general technique applied to any signal that carries unwanted high-frequency or low-frequency disturbances. It applies not just to sensors, but also to communication lines, power supplies, audio systems, and digital circuits. In simple terms, signal conditioning is preparing a sensor signal that may include noise filtering. Noise filtering is removing unwanted parts of any signal, whether from a sensor, a circuit, or a communication system. So in this lecture, we'll focus directly on the role of simple first-order filters in removing noise from signals, understand why noise occurs, and learn how to build practical circuits to reduce it. You'll find the technique I'm about to explain very familiar. As we discussed earlier, noise is any unwanted, unpredictable, or random signal that gets added to the signal that you care about. Sources of noise include electromagnetic interference from nearby equipment, power supply fluctuations, thermal noise generated by resistors, switching noise from digital circuits, and environmental factors such as vibrations or radio waves. Noise can make a clean signal appear distorted, jumpy, or unstable. If it isn't properly controlled, noise can cause errors in measurements, lost data in communications, or unpleasant distortion in audio systems. If you followed the course so far, you know what I'm about to explain. First-order filters like simple RC, low-pass, and high-pass circuits are a powerful first defense against noise. A low-pass filter can remove high-frequency noise, such as electromagnetic interference or fast digital switching, and a high-pass filter can remove low-frequency noise, like power line hum and slow drifts. The most important decision for designing a noise filter is to choose the right cutoff frequency. Here's two rules of thumb. Set the cutoff frequency just above the highest frequency of interest for low-pass to reject higher frequency noise. Set the cutoff frequency just below the lowest frequency of interest for high pass to reject lower frequency disturbances. Here, by frequency of interest, I mean the part of the signal spectrum that contains the useful or desired information. It's what you want to keep when designing a filter. The first-order filter acts like a soft barrier, allowing the useful part of the signal to pass through while gradually reducing unwanted noise. The first-order filter acts like a soft barrier, allowing the useful part of the signal to pass through while gradually reducing unwanted noise components. Here's what to remember from this lecture before going to the practical exercise in the next lecture. Noise is any unwanted random signal added to the useful signal. First-order RC filters are effective tools for reducing both high-frequency and low-frequency noise. Choosing an appropriate cutoff frequency is key to filtering out noise while preserving important signal information. And of course, practical simulations, and in my opinion, even more important, breadboard hands-on experiments help you experience the power of filtering firsthand. So in the next lecture, we'll go through an activity to show you just that.